Light years. The distance that breaks our brains. It's a measurement so vast, so impossibly large, that even saying the words out loud doesn't quite capture the sheer cosmic scale we're talking about. Think about it for a moment. When you walk to your mailbox, you cover maybe 100 feet. When you drive to work, perhaps 10 or 20 miles. When you fly across the country, a few thousand miles. These are distances your mind can handle, distances you can visualize, picture in your head with some degree of accuracy. But a light year, that's where everything falls apart. That's where our everyday understanding of distance completely collapses under the weight of the numbers involved. And tonight, we're going to rebuild that understanding piece by piece, taking a journey that will stretch from your backyard all the way to the very edge of everything we can possibly see. By the time we're done, you'll never look at the night sky the same way again. Let's start with something familiar, something comfortable. Imagine you're walking at a normal pace, maybe 3 miles per hour. That's the speed of a casual stroll, the kind of pace you might use when walking your dog or wandering through a park on a Sunday afternoon. At that speed, it would take you about 8 hours to walk a marathon. Now, let's speed things up. Get in a car on the highway, and suddenly you're moving at 60 or 70 miles per hour. The landscape blurs past your window. What took hours to walk now takes minutes to drive. You feel fast. You feel like you're covering serious ground, but you're not. Not really. Not compared to what's coming. Jump on a commercial jet, and now you're cruising at about 550 miles per hour. The ground below looks like a map. Clouds drift beneath you. You can cross an entire continent in a few hours, coast to coast, watching the sun move across the sky as you chase it westward. This feels incredibly fast. This feels like the upper limit of speed, the kind of velocity that makes your stomach drop during takeoff and landing. But we're not even close. We're not even scratching the surface, because now we need to talk about the speed of light. Light moves at exactly 186,282 miles per second. Not per hour, per second. Let that sink in for a moment. In the time it takes you to blink, light has already traveled thousands of miles. In the time it takes your heart to beat once, light has circled the Earth multiple times over. It is the fastest thing in the universe. Nothing can move faster. Nothing. It's not just a speed limit, it's the speed limit. The ultimate cosmic boundary that governs everything from the smallest particles to the largest galaxies. And here's the wild part. Light doesn't accelerate to this speed. It doesn't build up momentum like a car or a plane. The moment light exists, the moment a photon is born, it's already moving at this incredible velocity. It never speeds up. It never slows down. It just is. And that constancy, that unwavering, unchanging speed, is what makes it so perfect for measuring the truly vast distances in space. Because when you're dealing with the cosmos, miles and kilometers become laughably inadequate. They're too small, too clunky, too tied to our little planet and our little human scale. We needed something bigger. We needed a unit of measurement that could handle the enormity of the universe. And so we created the light year. But here's where things get interesting, where your brain starts to do that little flip that makes you pause and think, wait, what? A light year isn't just a measure of distance. It's also a measure of time. Think about it. Light takes time to travel. Not much time over short distances, but time nonetheless. When you look at the moon, you're not seeing the moon as it is right now. You're seeing the moon as it was about 1¼ seconds ago, because that's how long it took the light to travel from the moon to your eyes. The moon is about 238,000 miles away, and light, moving at its incredible speed, still needs over a second to make that journey. Now, a second isn't very long. You probably didn't even realize there was a delay, but that delay exists. And as we venture farther out into space, that delay gets longer and longer until we reach a point where we're not just looking across space, we're looking back in time. We're seeing the universe not as it is, but as it was. Every star in the night sky is a window into the past, a messenger from a time before you were born, before your parents were born, sometimes before our entire species even existed. And that's the real brain-breaking nature of the light year. It's a bridge between space and time, distance and history, turning astronomy into archaeology and making every glance at the heavens a journey backward through the ages. So let's define it precisely. 1 light year is the distance light travels in 1 year. Simple enough, right? But the numbers involved are staggering. Light moves at 186,282 miles per second. Multiply that by 60, and you get how far light travels in 1 minute. Multiply that by 60 again, and you get how far it travels in 1 hour. Multiply that by 24, and you get 1 day. Multiply that by 365, and you get 1 year. The final number is almost 6 trillion miles. That's 6 with 12 zeros after it. 5,878,625,373,183 miles, to be exact. That's 1 light year. And even trying to comprehend a trillion of anything is difficult enough. A trillion seconds ago, it was about 30,000 years in the past. A trillion miles is enough to circle the Earth 40 million times. And we're talking about almost 6 trillion miles. That's the distance light covers in a single year. And that's just the starting point. That's the baseline unit we use to measure cosmic distances. Because out there in space, 1 light year is actually quite short. It's a tiny hop, a small step, barely worth mentioning when you're talking about the scale of the galaxy, let alone the universe. But we're getting ahead of ourselves. We need to start small. We need to build up slowly. So let's begin right here, in our own solar system, using smaller units of light travel to wrap our heads around what we're dealing with. The moon, as we mentioned, is about 1¼ light seconds away. That means if you could somehow turn off the moon like flipping a light switch, you wouldn't see it disappear for 1¼ seconds. There would be a brief delay while the last photons of reflected sunlight made their way across the void to reach your eyes. It's a strange thought, isn't it? That there's a gap between what's happening and what you're seeing. A little slice of time embedded in the distance. Now let's go a bit farther. The Sun is 93 million miles from Earth, which translates to about 8 minutes and 20 seconds in light travel time. 8 light minutes. That's our next step up. When you look at the Sun, assuming you're using proper eye protection and not staring directly at it like some sort of cosmic daredevil, you're seeing the Sun as it was 8 minutes ago. If the Sun exploded right now, a cataclysmic event of unimaginable power and terror, we wouldn't know about it for 8 minutes. We'd go about our day, completely oblivious, until the last light from the Sun reached us, followed shortly by, well, the end of everything. But let's not dwell on apocalyptic scenarios. Let's stay positive. The point is, even within our solar system, light travel time matters. It creates a delay, a cushion between events and observation. Let's keep going outward. Mars, our neighboring planet, the red world that has captivated human imagination for centuries, sits at varying distances from Earth depending on where both planets are in their orbits. At its closest, Mars is about 34 million miles away, which is roughly 3 light minutes. At its farthest, when Earth and Mars are on opposite sides of the Sun, the distance balloons to about 250 million miles, or about 22 light minutes. This is why talking to a rover on Mars isn't like having a phone conversation. When Mission Control sends a signal to a Mars rover, they have to wait several minutes for that signal to arrive, and then several more minutes for the rover's response to come back. It's a conversation conducted in slow motion, each side waiting patiently for the other to speak across the gulf of space. And Mars is practically next door compared to what's coming next. Neptune, the farthest planet in our solar system since Pluto got demoted, sits about 2.7 billion miles from the Sun. That's about 4 light hours away. 4 hours. If you pointed a laser at Neptune, assuming you had a laser powerful enough to reach that far and precise enough to hit a target so distant, the light wouldn't arrive for 4 hours. And if Neptune somehow had a mirror and bounced that light back, you'd be waiting 8 hours for the round trip. That's a full workday of light travel just to say hello to the edge of our solar system. But even Neptune isn't the edge. Not really. Beyond Neptune lies the Kuiper Belt, a vast ring of icy objects that stretches out for billions of miles. And beyond that, the Oort cloud, a theoretical shell of comets and frozen debris that surrounds the entire solar system like a cosmic bubble. The Oort cloud is thought to extend out to nearly 2 light years from the Sun. 2 light years. That's almost 12 trillion miles, and we're still technically within the gravitational influence of our own star. The Sun's reach is far greater than most people realize, but 2 light years is also where we finally transition from our local neighborhood to the wider galaxy. Because just beyond the Oort cloud, just past that distant shell of ice and rock, we encounter our very first neighboring star. And this is where the light year truly begins to show its usefulness. Proxima Centauri, the closest star to our Sun, the nearest neighboring campfire in the cosmic night. It sits 4.24 light years away. 4.24 light years. That's about 25 trillion miles. If you got in the fastest spacecraft humans have ever built, the Parker Solar Probe, which can reach speeds of over 400,000 miles per hour when it's diving close to the Sun, it would still take you over 6,000 years to reach Proxima Centauri. 6,000 years. That's longer than recorded human history. That's back before the pyramids were built, before written language, before agriculture. You'd leave Earth, and by the time you arrived, assuming you somehow didn't age or die, human civilization would be completely unrecognizable. And that's just to reach the nearest star. But here's the really mind-bending part. When you look at Proxima Centauri through a telescope, you're not seeing it as it is today. You're seeing it as it was 4.24 years ago. The light that's hitting your eye right now, the photons that traveled across space to reach you, they began their journey over 4 years in the past. If Proxima Centauri exploded tomorrow, we wouldn't see it happen until 4 years from now. We'd be going about our lives, completely unaware that one of our closest neighbors had vanished in a blaze of cosmic fire. This is the light year's true power. It doesn't just measure distance, it measures history. It turns the universe into a time machine, with every star a postcard from the past. Proxima Centauri isn't alone. It's part of a triple star system called Alpha Centauri, which includes 2 other stars, Alpha Centauri A and Alpha Centauri B. These 2 are a bit farther away, about 4.37 light years, but still close enough to be considered our nearest neighbors. They're both sun-like stars, bright and warm, the kind of stars that could potentially have planets, maybe even planets with life. We don't know yet. But the point is, these stars are close. In cosmic terms, they're right next door, and yet they're still over 4 light-years away, still separated from us by trillions of miles and years of light travel time. This is the scale we're working with now. This is the new normal, and it only gets bigger from here. Let's venture a bit farther out, into what astronomers call our local stellar neighborhood, the bubble of space within a few dozen light-years of the Sun. This is our cosmic backyard, the stars you can see with your naked eye on a clear night, the ones that have names and stories and have guided human navigation for thousands of years. Sirius, for example, the brightest star in the night sky, the one that ancient Egyptians used to predict the flooding of the Nile, sits 8.6 light-years away. 8.6 light-years. That's about 50 trillion miles. When you look at Sirius twinkling in the winter sky, you're seeing light that left that star during the time you were probably in elementary school, assuming you're in your 20s now. If you're older, adjust accordingly. But the principle remains the same. Sirius is showing you its past, a version of itself from years ago, and by the time that light reaches your eyes, Sirius has already moved on, changed, evolved in ways we won't see for nearly a decade. Sirius is actually a binary star system, meaning it has a companion, a small white dwarf star called Sirius B that orbits around the brighter primary star. White dwarfs are the remnants of stars that have exhausted their fuel and collapsed down into incredibly dense objects about the size of Earth, but with the mass of the Sun. Sirius B is so dense that a teaspoon of its material would weigh several tons here on Earth. It's a glimpse into the future, a preview of what stars like our Sun will eventually become billions of years from now, when they run out of hydrogen to burn and begin their slow fade into the cosmic night. But we're not here to talk about stellar evolution, at least not yet. We're here to talk about distance, and Sirius, at 8.6 light-years, is just the beginning. Vega, another bright star, this one visible in the summer sky, sits 25 light-years away. 25 light-years. That's about 147 trillion miles. The light you see from Vega tonight left that star in the late 1990s, around the time the internet was just becoming mainstream and people were worried about the Y2K bug. Vega is a young star, only about 450 million years old, which in cosmic terms is practically a baby. It's also rotating incredibly fast, spinning so quickly that it's actually flattened at the poles and bulging at the equator, like a cosmic pancake. Astronomers discovered this by studying the light coming from different parts of the star and noticing that the poles are hotter and brighter than the equator, a telltale sign of rapid rotation. But again, all of this information, everything we know about Vega, is 25 years out of date. We're studying history, examining a star as it was a quarter century ago, because that's how long it took the light to reach us. Arcturus, a giant orange star visible in the spring, sits 37 light-years away. 37 light-years. That's over 217 trillion miles. Arcturus is old and evolved, a red giant that has exhausted the hydrogen in its core and is now burning helium, puffing up to enormous size in the process. It's about 25 times larger than the Sun, and if you placed it where our Sun is, its surface would extend past the orbit of Mercury. It's the kind of star our Sun will become someday, far in the future, when it too runs out of fuel and begins its transformation into a giant. But Arcturus is showing us its past from the mid-1980s, back when personal computers were just starting to appear in homes and the Cold War was still a defining feature of global politics. That's how far away 37 light-years really is. It's not just distance, it's time, history, a window into a world that no longer exists except in the light traveling toward us. And we can keep going. Altair, 12 light-years away. Pollux, 34 light-years. Deneb, one of the most distant stars visible to the naked eye, sits somewhere between 1,400 and 3,000 light-years away. The uncertainty in that number should tell you something about the challenges of measuring cosmic distances. Even with all our technology, all our telescopes and satellites and sophisticated instruments pinning down the exact distance to faraway stars remains difficult. But let's focus on Deneb for a moment, because it represents a massive leap in scale. 1,400 to 3,000 light-years. That means the light we see from Deneb left that star sometime between the year 600 and the year 1400 AD. When that light began its journey, the Roman Empire had collapsed, the Dark Ages were in full swing, and the Americas had not yet been discovered by Europeans. That light has been traveling through space for over 1,000 years, crossing incomprehensible distances, and it's only just now arriving at Earth, only now reaching your eyes as you look up at the night sky. Deneb is showing you the medieval world, a time of knights and castles, and plague, all encoded in photons that have journeyed across the galaxy to reach you. This is what a light year means at a practical level. It means that astronomy is always historical. There is no such thing as observing the universe as it is right now. We can only see the universe as it was at various points in the past, depending on how far away we're looking. The farther out we go, the further back in time we travel, until we reach a point where we're seeing the universe not as it was yesterday or last year or even last century, but as it was billions of years ago in its infancy, when stars were just beginning to form and galaxies were young and chaotic. But we're not there yet. We're still in our local neighborhood, still within a few dozen light years of home. Let's keep expanding. Within about 30 light years of the Sun, there are roughly 400 stars. Some are bright and massive, others are dim and small. Some are single stars like our Sun, while others are part of binary or even triple star systems, locked in gravitational dances that have lasted for billions of years. The nearest of these stars, Proxima Centauri, we've already discussed, but there are others worth mentioning. Barnard's star, for example, sits just 6 light years away and is one of the fastest moving stars in our sky, racing through space at about 87 miles per second relative to the Sun. In about 10,000 years, Barnard's star will be our closest neighbor, briefly surpassing Proxima Centauri before continuing on its journey through the galaxy. Then there's Wolf 359, a tiny red dwarf star about 7.8 light years away, so dim that you need a telescope to see it, despite it being one of our closest neighbors. Red dwarfs are the most common type of star in the galaxy, making up about 70% of all stars. But they're so faint that not a single one is visible to the naked eye from Earth. They burn their fuel slowly, sipping hydrogen over trillions of years, far longer than the current age of the universe. Stars like Wolf 359 will outlive everything else, glowing dimly long after larger, brighter stars like the Sun have burned out and faded away. These nearby stars, this collection of suns within a few light years of our own, form a loose bubble of stellar neighbors, a small cluster in the vastness of the galaxy. But this bubble, this comfortable little region of space we call home, is just one tiny neighborhood in a much larger city, because our Sun isn't floating alone in empty space. It's part of a structure, a spiral arm of the Milky Way galaxy called the Orion Arm, or sometimes the Orion Spur. This arm is a branch off one of the galaxy's main spiral arms, a ribbon of stars and gas and dust that stretches for thousands of light years through space. And within this arm, stars are clustered together in rough groupings, pockets of higher density surrounded by voids of relative emptiness. Our Sun sits in one of these pockets, along with hundreds of other stars, forming a loose association that moves through the galaxy together, all of us orbiting the galactic center in a slow, stately procession that takes about 225 million years to complete. That's one galactic year. The last time the Sun was in this exact position in its orbit, dinosaurs were just beginning to appear on Earth. The next time it comes around, humanity will likely be long gone, replaced by whatever species or intelligence evolves to take our place. But let's not get distracted by deep time and evolutionary speculation. Let's stay focused on distance, because we're about to make a big jump from dozens of light years to thousands of light years, from our local neighborhood to the broader structure of the galactic disk. This is where things start to get truly enormous, where the numbers become so large that even trying to visualize them feels futile. But we're going to try anyway. We're going to push through step by step, building our understanding one layer at a time until we've covered the entire observable universe. And the next stop on our journey is the center of the galaxy itself, the dense, crowded heart of the Milky Way, where millions of stars cluster together around a supermassive black hole with a mass equal to 4 million suns. It's called Sagittarius A star, and it sits 26,000 light years from Earth. 26,000 light years. Let that number wash over you for a moment. 26,000 light years is about 153 quintillion miles. That's a 1 followed by 18 zeros. It's a number so large that trying to comprehend it in terms of miles or kilometers is essentially meaningless. The only way to grasp it is through time, through the understanding that the light we see from the galactic center left that region 26,000 years ago, during the last ice age, when woolly mammoths still roamed the Earth and humans were just beginning to develop agriculture. The light from the center of our galaxy has been traveling through space for longer than recorded history, longer than civilization, longer than any human structure or monument has existed. It's been crossing the void between stars, threading through clouds of gas and dust, dodging asteroids and comets and planets, all while maintaining its speed, its direction, its unwavering commitment to reaching Earth. And now, tonight, that light is finally arriving, finally completing its journey, hitting your retinas and allowing you to see the galactic center as it was during the Stone Age. But here's something interesting. We can't actually see the galactic center with our eyes. It's hidden behind thick clouds of dust and gas that block visible light, creating a dark band across the middle of the Milky Way when you look at it from a dark sky location. To peer into the heart of the galaxy, astronomers have to use infrared light, which can penetrate the dust, or radio waves, which pass through it entirely. These observations have revealed a chaotic, violent place, a region where stars are packed so tightly together that they're only light weeks or light months apart, compared to the light years of separation we have here in the galactic suburbs. Near the center, stars are constantly interacting, their gravitational fields tugging and pulling on each other, occasionally flinging a star out of the galaxy entirely, or sending it plunging into the black hole at the center. Sagittarius A star itself is a monster, a fair black hole so massive that its event horizon, The point of no return, beyond which nothing can escape, is about 17 times larger than the Sun. It's quiet now, relatively dormant, but there's evidence that in the past it was much more active, consuming nearby stars and gas in violent feeding frenzies that lit up the entire galaxy. And all of this, every detail we know about the galactic center, is information from 26,000 years ago. By now, by the actual present moment, the galactic center has changed in ways we won't see for millennia. Let's zoom out even further, looking not just at the center, but at the entire structure of the Milky Way galaxy. Our galaxy is shaped like a disk with a central bulge, a flattened spiral of stars that spans about 100,000 light years from edge to edge. 100,000 light years. That's about 588 quadrillion miles, a number so absurdly large that it's effectively meaningless in any practical sense. But let's try to break it down. If you stood on one edge of the Milky Way and looked across to the other side, the light you'd see from those distant stars left them 100,000 years ago, back when Homo sapiens were just emerging as a distinct species in Africa, before we'd spread across the globe, before we'd developed language or art, or any of the things that make us recognizably human. The Milky Way, in other words, is so large that no single observer could ever see it as a unified whole. Every part of it exists at a different point in time, with the near side showing recent history and the far side showing ancient history, and everything in between representing various moments across the span of 100 millennia. The Milky Way isn't just a flat disk, though. It has depth, structure, layers that extend above and below the main plane. There's the thin disk, where most of the stars are concentrated, including our Sun. Then there's the thick disk, a more diffuse layer of older stars that orbits at different angles and speeds. And finally, there's the halo, a roughly spherical region that surrounds the entire galaxy and extends out to about 130,000 light years from the center, maybe even farther. The halo is a strange place, home to some of the oldest stars in the galaxy, ancient suns that formed when the Milky Way itself was young and still taking shape. These stars are found in dense clusters called globular clusters, tightly packed balls of stars that orbit through the halo like bees around a hive. Each globular cluster contains hundreds of thousands to millions of stars, all crammed into a sphere only a few dozen light years across. Inside a globular cluster, stars are separated by mere light weeks or light days, so close together that their night skies would be ablaze with thousands of brilliant points of light, a spectacle unlike anything we can see from Earth. One of the most famous globular clusters, Messier 13, sits about 22,000 light-years away, roughly the same distance as the galactic center, but in a completely different direction, up above the galactic plane. When you look at Messier 13 through a telescope, you're seeing a swarm of stars as they were during the last ice age, each one a sun in its own right, each one potentially surrounded by planets and moons and asteroids. The combined light of all those stars, hundreds of thousands of them packed together, traveled for 22,000 years to reach your eyes, carrying information about a time when humans were hunter-gatherers and the idea of civilization was still tens of thousands of years in the future. Another cluster, Omega Centauri, is even more impressive, containing about 10 million stars and sitting about 16,000 light-years away. It's so large and so massive that some astronomers think it might actually be the remnant core of a small galaxy that was torn apart and absorbed by the Milky Way billions of years ago. If that's true, then Omega Centauri is a fossil, a relic of an ancient cosmic collision, and the light we see from it is a message from that distant, violent past. But the halo isn't just stars, it's also dark matter. Lots and lots of dark matter. Dark matter is one of the greatest mysteries in modern astronomy, a substance that makes up about 85% of all the matter in the universe, but doesn't emit, absorb, or reflect light. We can't see it directly. We can only detect it through its gravitational effects, the way it pulls on visible matter and bends light from distant galaxies. And those effects tell us that the Milky Way is embedded in a massive halo of dark matter that extends far beyond the visible edge of the galaxy, perhaps out to 600,000 light-years or more. That's 6 times larger than the visible galaxy, a vast invisible structure that outweighs all the stars, gas, and dust in the Milky Way combined. This dark matter halo is what holds the galaxy together, providing the gravitational glue that keeps everything from flying apart as the galaxy rotates. Without it, the outer regions of the galaxy would be spinning so fast that stars would be flung out into intergalactic space like water flying off a spinning wheel. But dark matter keeps everything in check, its invisible mass exerting a gentle but persistent pull that maintains the galaxy's structure. Scientists don't know what dark matter is made of. It's not normal atoms, not protons and neutrons and electrons like everything we're familiar with. It's something else, some exotic particle that interacts with normal matter only through gravity, passing through everything else like a ghost. There are experiments deep underground, shielded from cosmic rays and radiation, trying to detect dark matter particles as they drift through the Earth, but so far those experiments have found nothing. Dark matter remains stubbornly hidden, a presence felt but not seen, a shadow that shapes the universe without revealing itself. And yet, despite not knowing what it is, we know it's there. The evidence is overwhelming, written in the rotation curves of galaxies and the motion of galaxy clusters and the bending of light around massive structures. Dark matter is real, and it's everywhere, including right here, right now, passing through your body at this very moment. Billions of dark matter particles flowing through you like you're not even there. It's an eerie thought, isn't it? That the universe is full of invisible matter, an entire, hidden dimension of reality that we can only perceive through its effects on the things we can see. But let's leave the dark matter mystery for the moment and return to the visible galaxy, because we've established the scale of the Milky Way now. We've gone from our sun, a single star, to our local neighborhood of a few dozen stars, to the galactic disk with its 100 billion suns, to the halo and its ancient globular clusters. We've covered distances from a few light years to 100,000 light years, from human timescales to ice age timescales, from the recent past to the deep past. But the Milky Way, enormous as it is just one galaxy among hundreds of billions in the observable universe. And it's time now to take the next big step, to leave our home galaxy behind and venture out into intergalactic space, into the vast dark voids between galaxies where distances are measured not in thousands of light years, but in millions and billions. This is where the light year truly becomes the only meaningful unit of measurement, where everything else falls away and we're left with nothing but time and distance, history and space, all woven together into a single unified tapestry. The first stop outside the Milky Way is actually not that far, cosmically speaking. The large Magellanic Cloud, a small irregular galaxy that orbits the Milky Way like a satellite, sits about 160,000 light years away. 160,000 light years. That's about 940 quintillion miles. The light we see from the Large Magellanic Cloud left that galaxy 160,000 years ago, long before modern humans had spread out of Africa, back when Neanderthals still walked the Earth and the last ice age was just beginning. The Large Magellanic Cloud is visible from the southern hemisphere as a faint smudge in the night sky, a ghostly patch of light that looks almost like a piece of the Milky Way that broke off and drifted away. And in a sense, that's not far from the truth. The Large Magellanic Cloud is being slowly torn apart by the Milky Way's gravity, its stars and gas being stripped away and absorbed into our galaxy, a process that will eventually consume it entirely billions of years from now. But right now, in the light we're seeing, which is 160,000 years old, the Large Magellanic Cloud is still intact, still a distinct entity, still going about its cosmic business unaware of the fate that awaits it. Accompanying the Large Magellanic Cloud is its smaller companion, the aptly named Small Magellanic Cloud, which sits about 200,000 light-years away. Both of these galaxies are visible to the naked eye from the southern hemisphere and have been known to human cultures for thousands of years. Ancient navigators used them as guideposts, and various indigenous peoples incorporated them into their mythologies and stories. But it wasn't until the 20th century that astronomers realized these clouds weren't just nebulae or clusters of stars within the Milky Way. They were separate galaxies entirely, distinct islands of stars orbiting our own. This realization was part of a broader revolution in astronomy that occurred in the early 1900s, when scientists finally understood that the universe was far, far larger than anyone had previously imagined, filled with countless galaxies scattered across unimaginable distances. Before that, many astronomers thought the Milky Way was the entire universe, that nothing existed beyond our galaxy. It was only through careful observation and measurement, particularly the work of astronomers like Henrietta Leavitt and Edwin Hubble, that the true scale of the cosmos became apparent. Now, let's make a bigger jump. Let's leap across 2.5 million light-years of space to reach the Andromeda galaxy, the nearest large galaxy to the Milky Way and our ultimate cosmic neighbor. 2.5 million light-years. That's about 14 sextillion miles, a number with 21 zeros. It's so large that even light, traveling at its incredible speed, needs 2.5 million years to cross the distance. Think about what that means. The light we see from Andromeda tonight left that galaxy 2.5 million years ago, back when our ancestors were primitive hominids, early members of the genus Homo, just beginning to use stone tools and figure out how to survive in the African wilderness. There were no cities, no agriculture, no written language, no art. Humans as we know them didn't exist yet, and that light had been traveling ever since, crossing the void between galaxies, passing through intergalactic space, a realm so empty that there's on average less than 1 atom per cubic meter, a vacuum more perfect than anything we can create in a laboratory. For 2.5 million years, those photons have journeyed through the darkness, and now, tonight, they're reaching Earth, hitting your eyes, allowing you to see a galaxy as it was in the Pliocene epoch, a time when the Earth was warmer, the ice caps were smaller, and the continents were still slowly drifting toward their current positions. Andromeda is spectacular. It's larger than the Milky Way, containing about 1 trillion stars compared to our paltry 100 billion. It has a bright central bulge, graceful spiral arms, and its own retinue of satellite galaxies, smaller galaxies that orbit around it, just like the Magellanic Clouds orbit the Milky Way. If you go to a dark sky site, far from city lights, and look toward the constellation Andromeda on a clear autumn night, you can see it with your naked eye. A faint oval smudge that doesn't look like much, but is actually a trillion suns. A galaxy roughly the same size as our own, suspended in space, 2.5 million light-years away. It's the farthest object visible to the naked eye, the most distant thing a human can see without the aid of telescopes or binoculars. And yet it's also one of our closest neighbors, part of what astronomers call the local group, a collection of about 80 galaxies bound together by gravity, including the Milky Way, Andromeda, the Magellanic Clouds, and dozens of smaller dwarf galaxies scattered throughout the region. The local group spans about 10 million light-years across, a vast bubble of space containing all these galaxies, and it's moving through the universe as a single unit, pulled along by the gravity of even larger structures beyond. But within the local group, galaxies are also moving relative to each other, orbiting around common centers of mass, tugged and pulled by their mutual gravitational attraction. The Milky Way and Andromeda, for example, are actually moving toward each other, falling together at a speed of about 70 miles per second. In about 4 billion years, they'll collide, merging together in a spectacular cosmic train wreck that will reshape both galaxies, flinging stars out into space, triggering massive bursts of star formation, and eventually creating a single giant elliptical galaxy that astronomers have already nicknamed Milkomeda. But that collision is billions of years in the future. For now, Andromeda and the Milky Way are still separate, still distinct, still two galaxies among many in a universe filled with islands of stars. Let's pause here for a moment to reflect on what we've covered so far. We started at the Moon, 1.25 light seconds away. We moved to the Sun, 8 light minutes distant, then to the edge of the solar system, a few light hours out, then to the nearest stars, a few light years, then to the galactic center, 26,000 light years, then to the edge of the Milky Way, 100,000 light years, and now we've reached Andromeda, 2.5 million light years away. Each step has been bigger than the last, each jump spanning more distance and more time. And yet, we're still relatively close to home. The local group is a tiny corner of the universe, a small collection of galaxies huddled together in a cosmos filled with billions of such groups. To truly understand the scale of the universe, we need to go even farther, out beyond the local group, into the realm of galaxy clusters and superclusters, vast cosmic structures that span hundreds of millions of light years. This is where the universe reveals its true architecture, its grand design, and where the light year becomes not just a measure of distance, but a key to understanding the history and evolution of everything that exists. Beyond the local group, the universe is organized into larger and larger structures, a hierarchy of cosmic architecture that scales up from individual galaxies to clusters of galaxies to superclusters, to even vaster filaments and walls. The nearest large galaxy cluster to us is the Virgo cluster, a massive collection of about 2,000 galaxies located roughly 55 million light-years away. 55 million light-years. We've jumped from millions to tens of millions, from the recent prehistoric past to a time when the Earth was very different. 55 million years ago, the dinosaurs had been extinct for about 10 million years. Mammals were diversifying, spreading across the continents, evolving into all sorts of strange and wonderful forms. The climate was warmer. Forests covered regions that are now deserts. The ancestors of modern horses were the size of dogs. And in space, light was leaving the Virgo cluster, beginning its long journey across the cosmos toward a small blue planet orbiting an unremarkable yellow star in a distant corner of a distant galaxy. That light has been traveling ever since, crossing the void, maintaining its speed and direction, until finally, tonight, it reaches Earth. The Virgo cluster is enormous, spanning about 15 million light-years across and containing galaxies of all shapes and sizes. There are giant elliptical galaxies, smooth and featureless, made up mostly of old stars and lacking the gas and dust needed to form new ones. There are grand spiral galaxies like our own Milky Way, with graceful arms and active star formation. There are peculiar galaxies, misshapen and irregular, often the result of past collisions or gravitational interactions. And at the heart of the cluster sits Messier 87, a supergiant elliptical galaxy that contains several trillion stars and hosts one of the most massive black holes ever discovered, a monster with a mass equal to 6.5 billion suns. This black hole is so enormous that its event horizon is about the size of our entire solar system out to Pluto, and it's active, consuming nearby gas and matter, firing jets of particles and radiation out into space at nearly the speed of light. These jets are so powerful and so energetic that they can be detected across the electromagnetic spectrum, from radio waves to X-rays. In 2019, the Event Horizon Telescope, a global network of radio dishes working together, captured the first ever image of a black hole's shadow. And that black hole was the one at the center of Messier 87. The image showed a bright ring of light surrounding a dark circle, the shadow of the event horizon, and it was a triumph of modern astronomy, a confirmation that black holes really do exist and really do match the predictions of Einstein's general relativity. But that image shows the black hole as it was 55 million years ago. The actual present-day state of that black hole, what it's doing right now, won't be visible to us for another 55 million years. The Virgo cluster is part of an even larger structure called the Virgo supercluster, which includes the local group and dozens of other galaxy groups and clusters, spanning about 110 million light-years across. 110 million light-years. At this scale, we're looking back to a time when the first primates were appearing on Earth, small tree-dwelling mammals with grasping hands and forward-facing eyes. The continents were still moving toward their current positions. India was crashing into Asia, pushing up the Himalayas. North America and Europe were drifting apart, widening the Atlantic Ocean, and the light that's now reaching us from the far edge of the Virgo supercluster left back then, carrying information about galaxies as they were during the Cretaceous period, shortly after the extinction event that wiped out the dinosaurs. It's a humbling thought, isn't it? That we're seeing the universe not as a single unified present, but as a collection of different pasts, each one frozen at a particular moment in history, depending on how far away it is. But even the Virgo supercluster isn't the largest structure we can identify. In recent decades, astronomers have discovered that the universe is organized on even grander scales, with superclusters arranged in vast filaments and walls that stretch for hundreds of millions or even billions of light-years. These structures form what's called the cosmic web, a foam-like pattern of matter that looks like a gigantic three-dimensional spider web, with dense filaments of galaxies separated by enormous voids where very few galaxies exist. The filaments contain most of the galaxies in the universe, strung along like beads on a string, while the voids are vast, empty regions that can span hundreds of millions of light-years with almost nothing inside them. This cosmic web is the result of how the universe evolved how tiny fluctuations in the density of matter shortly after the Big Bang grew over billions of years into the structures we see today. Gravity pulled matter together in some regions, creating filaments and clusters, while leaving other regions relatively empty, creating voids. And this pattern, this web, is visible across the entire observable universe, a testament to the fundamental processes that shape the cosmos. One of the largest structures ever discovered is the Hercules Corona Borealis Great Wall, a vast filament of galaxies that spans about 10 billion light years. 10 billion light years. It's so large that it challenges our understanding of how the universe should be organized. According to cosmological models, structures this big shouldn't exist. The universe hasn't been around long enough for gravity to pull together something that massive. And yet, there it is, stretching across a significant fraction of the observable universe, a wall of galaxies that defies explanation. Or consider the Botez Void, a nearly empty region of space about 330 million light-years across that contains only about 60 galaxies, compared to the thousands or tens of thousands you'd expect in a typical region of that size. It's sometimes called the Great Nothing, and it's so empty, so devoid of galaxies, that astronomers are still trying to figure out how it formed. Did something push the galaxies out? Did they never form there in the first place? The answers remain uncertain, and the void stands as a reminder that despite all our advances in astronomy, there's still so much we don't understand about the universe. But let's return to the concept of distance and time, because we've been talking about hundreds of millions of light years, which means we're looking back hundreds of millions of years into a time when the Earth was very different. 300 million years ago, the supercontinent Pangaea was forming. The first reptiles were evolving. Ferns and mosses dominated the land, and light was leaving distant galaxy clusters, beginning its journey toward Earth. That light has been traveling ever since, crossing the expanding space of the universe, and it's only now arriving, only now reaching our telescopes, allowing us to see those galaxies as they were in the Carboniferous period, when coal was being formed from vast swamp forests and insects grew to enormous sizes in the oxygen-rich atmosphere. Every photon carries information, a snapshot of the universe at a particular moment, and by collecting and studying those photons, astronomers can piece together the history of the cosmos, tracing its evolution from the distant past to the present. As we continue outward, beyond a few 100 million light years, the effects of cosmic expansion become more noticeable. The universe is expanding, with space itself stretching, carrying galaxies along with it. This expansion was discovered in the 1920s by Edwin Hubble, who noticed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship, known as Hubble's law, tells us that the universe is not static but dynamic, growing larger with each passing moment. And this expansion has profound implications for how we measure distance at cosmological scales. When we say a galaxy is 1 billion light years away, we mean the light from that galaxy has been traveling for 1 billion years. But during that time, space has been expanding, so the galaxy is actually much farther away now than it was when the light left. In other words, distance in the universe is not a fixed, unchanging quantity. It's something that evolves over time, making cosmology both fascinating and complicated. At 1 billion light years, we're looking back 1 billion years to a time when the Earth was in the midst of the Proterozoic eon, when life consisted primarily of simple single-celled organisms and the atmosphere was just beginning to accumulate oxygen from photosynthetic bacteria. The first multicellular life was still hundreds of millions of years in the future. And yet, in distant galaxies, stars were forming, planets were coalescing, and the processes that would eventually lead to complex chemistry and maybe even life were already underway. The universe was busy, active, full of energy and transformation, and the light from those events has been traveling toward us ever since, a message from a time when the Earth was young and the cosmos was very different from what it is today. At 2 billion light years, we're seeing the universe as it was 2 billion years ago, during the Paleoproterozoic era, when the first large continents were forming and the Great Oxidation Event was transforming the atmosphere, paving the way for more complex life to evolve. At 5 billion light years, we're looking back to a time before the Earth even existed, before the solar system formed, when the region of space that would eventually become our home was nothing but a cloud of gas and dust drifting through the galaxy. In 10 billion light years, we're seeing galaxies as they were 10 billion years ago, when the universe was only about 3 billion years old, a wild, chaotic place with much higher rates of star formation, more frequent galaxy collisions, and a very different large-scale structure. These distant galaxies are often blue and irregular, full of hot, young stars, lacking the graceful spiral shapes and smooth, elliptical forms that are more common in the nearby universe. They're younger, rawer, more energetic, and studying them helps astronomers understand how galaxies evolve over cosmic time, how they grow and change, and eventually settle into the forms we see today. And we can go even farther. At 12 billion light years, we're approaching the limits of what our best telescopes can see, peering back to a time when the universe was less than 2 billion years old. At this distance, galaxies are just beginning to take shape, forming out of the primordial gas that filled the early universe. Stars are being born at prodigious rates, creating the first heavy elements through nuclear fusion and spreading them into space when they die in supernova explosions. At 13 billion light years, we're seeing some of the very first galaxies that ever formed, small, irregular collections of stars that would eventually merge and grow into the larger galaxies we see today. These galaxies are so faint, so distant, that detecting them requires the most powerful telescopes ever built, instruments like the James Webb Space Telescope, which was specifically designed to peer into the early universe and capture light from the first generation of stars and galaxies. And what Webb has found is astonishing. It's revealed galaxies that are larger and more mature than expected at such early times, galaxies that challenge our models of how structure forms in the universe. It's also found incredibly distant supermassive black holes with millions or even billions of solar masses that somehow formed when the universe was only a few 100 million years old, far too quickly according to our current theories. These discoveries are forcing astronomers to rethink how the early universe worked, how galaxies and black holes grew so rapidly, and what processes were at play during those first crucial billion years after the Big Bang. But there's a limit to how far we can see. No matter how powerful our telescopes become, there's a boundary beyond which we cannot peer, a horizon imposed not by technology, but by the fundamental nature of the universe itself. This horizon is the edge of the observable universe, and it corresponds to the cosmic microwave background, the oldest light in existence. The cosmic microwave background, often abbreviated as CMB, is the afterglow of the Big Bang itself, a faint wash of radiation that fills the entire universe and comes from every direction in the sky. It was created about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light could finally travel freely through space. Before that moment, the universe was a hot, dense plasma, opaque to light, with photons constantly scattering off free electrons like people trying to walk through a thick fog. But when the temperature dropped below a certain threshold, electrons combined with protons to form hydrogen atoms, and suddenly the fog cleared. The universe became transparent, and light could travel across it without being absorbed or scattered. That light, the first light to freely traverse the cosmos, has been traveling ever since, and it's that light we detect today as the cosmic microwave background. When that light was emitted, 13.8 billion years ago, give or take a few tens of millions of years, it was hot and bright, in the visible spectrum, glowing orange and red like a cooling ember. But as the universe expanded, the light was stretched, its wavelength increasing, shifting from visible light to infrared to microwave. Today, the CMB has a temperature of about 2.7 degrees above absolute zero, and it peaks in the microwave portion of the electromagnetic spectrum, hence the name. It's everywhere, filling all of space. A uniform background glow that's the same in every direction to an incredible degree of precision. If you built a microwave detector and pointed it at the sky, you'd see the CMB, a faint signal that's been traveling for nearly 14 billion years, the oldest light in the universe, the edge of what we can possibly observe. The distance to the CMB is often given as 13.8 billion light years, because the light has been traveling for 13.8 billion years. But here's where things get tricky. During that time, the universe has been expanding. The region of space where the CMB was emitted, the hot plasma that filled the early universe, was much closer to us back then than it is now. In fact, when that light was emitted, the region where Earth would eventually form was only about 42 million light years away from the edge of the observable universe. But as the universe expanded, that distance grew. Today, the actual distance to the surface where the CMB was emitted is about 46 billion light years. 46 billion light years. That's the radius of the observable universe, the farthest distance we can possibly see, and it's much larger than 13.8 billion light years because of cosmic expansion. So when astronomers talk about the edge of the observable universe, they're talking about two different distances: the light travel distance, which is how long the light has been traveling, and the co-moving distance, which is how far away the source is now, taking expansion into account. Both numbers are correct, they're just measuring different things, and it's important to understand the distinction. At 46 billion light years, we've reached the edge of the observable universe, the boundary beyond which we cannot see, not because there's nothing there, but because light from farther away hasn't had time to reach us yet. The universe is 13.8 billion years old, so light can only have traveled for 13.8 billion years, and anything beyond that is, for now, invisible. But that doesn't mean the universe ends at the edge of the observable region. In fact, the universe is almost certainly much, much larger than what we can see. It might even be infinite, stretching on forever in all directions, filled with galaxies and stars and planets beyond our horizon, all of it forever hidden from view because the light hasn't reached us, and, due to the accelerating expansion of the universe, never will. This is one of the most profound and unsettling realizations in all of cosmology, that there are parts of the universe we can never observe, regions of space that are forever beyond our reach, no matter how long we wait or how advanced our technology becomes. The observable universe is just a bubble, a sphere of space centered on Earth, containing everything we can possibly see, but surrounded by an unimaginably vast, perhaps infinite expanse that remains forever mysterious. Let's think about what this means in practical terms. The CMB, that ancient light from the early universe, represents a wall, a barrier we cannot see past. It's like trying to see through a fog. Before the CMB was emitted, the universe was opaque, filled with hot plasma, and no light could travel through it, so we can't see anything from before that moment. The first 380,000 years of the universe's history are hidden from us, at least in terms of visible light and electromagnetic radiation. However, scientists have other ways to probe that early period. Gravitational waves, for example, can travel through the opaque plasma, and future detectors might be able to pick up gravitational wave signals from the very first moments after the Big Bang. There's also the cosmic neutrino background, a sea of neutrinos that were produced even earlier than the CMB, and could, in principle, give us information about the universe when it was only about 1 second old. But detecting those neutrinos is incredibly difficult, far beyond our current technology. So for now, the CMB remains our primary window into the early universe. The CMB is remarkably uniform, with the same temperature in all directions to about 1 part in 100,000. But there are tiny fluctuations, small variations in temperature that correspond to regions of slightly higher or lower density in the early universe. These fluctuations are the seeds of all the structure we see today, the galaxies, clusters, and superclusters. Regions that were slightly denser had a bit more gravity, and over time, they pulled in more matter, growing into the galaxies and galaxy clusters that fill the universe today. By studying the pattern of these fluctuations in the CMB, astronomers can learn about the conditions in the early universe, the amount of normal matter versus dark energy, the rate of expansion, and even the overall geometry of space. The CMB is a treasure trove of information, a snapshot of the universe when it was less than 400,000 years old, and it's one of the most important pieces of evidence we have for the Big Bang theory. But we still haven't fully grasped the scale of what we're talking about. 13.8 billion light years, or 46 billion light years if we account for expansion, is a distance so vast that it's almost meaningless in any practical sense. Let's try to put it in perspective. If you could travel at the speed of light, it would take you 13.8 billion years to reach the edge of the observable universe. That's longer than the current age of the Earth, longer than the time multicellular life has existed, longer than the time since the first stars formed. It's essentially forever in human terms, an eternity, an incomprehensible span of time during which entire civilizations could rise and fall, entire species could evolve and go extinct, entire planets could form and be destroyed. And that's just the observable universe, just the part we can see. The total universe, the actual size of all of space, could be vastly larger, perhaps infinite, filled with regions we'll never observe, galaxies and stars and worlds that are forever hidden beyond our horizon. Some cosmologists speculate that the universe might not just be infinite in extent, but also infinite in content, meaning there could be other regions of space, far beyond our observable bubble, where conditions are different, where the laws of physics might vary, where entirely different forms of matter and energy exist. This idea comes from certain models of cosmic inflation, the theory that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. According to inflation, different regions of space could have inflated by different amounts, creating a multiverse. a vast ensemble of bubble universes, each with its own properties and physical laws. Our observable universe would be just one bubble among countless others, separated by distances so enormous that they dwarf even the scale of the observable universe. This is all highly speculative, and there's no direct evidence for a multiverse. But it's a fascinating possibility, one that pushes the boundaries of what we can imagine and forces us to confront the limits of our knowledge. Even within the observable universe, there's so much we don't understand. Dark matter and dark energy together make up about 95% of the total mass energy of the cosmos, and we don't know what either of them is. Dark matter, as we've discussed, is invisible matter that interacts only through gravity. Dark energy is even stranger, a mysterious force that's causing the expansion of the universe to accelerate, pushing galaxies apart at ever-increasing speeds. It was discovered in the late 1990s when astronomers studying distant supernovae realized that the universe's expansion wasn't slowing down, as everyone had expected, but speeding up. This was a huge surprise, and it earned the discoverers the Nobel Prize. But it also raised more questions than it answered. What is dark energy? Where does it come from? Why does it have the value it does? These questions remain unanswered, and they represent some of the biggest mysteries in modern physics. Dark energy has profound implications for the future of the universe. If it continues to dominate, and current evidence suggests it will, then the universe will keep expanding forever, accelerating to the point where distant galaxies recede from us faster than the speed of light. Eventually, billions of years in the future, all the galaxies outside our local group will be pushed beyond our horizon, becoming forever invisible. The sky will grow dark as one by one the distant lights disappear, leaving us alone in a sea of blackness, with only the stars of our own galaxy for company, and even those stars will eventually burn out. In trillions of years, all the stars in the universe will have exhausted their fuel, leaving behind white dwarfs, neutron stars and black holes, and the universe will enter a long, slow decline into darkness and cold, a state known as the heat death of the universe. But that's so far in the future, so unimaginably distant, that it's not worth worrying about. For now, the universe is vibrant, full of light and energy and change, and we have the privilege of observing it, studying it, trying to understand its mysteries. So let's return to the light year, the unit of measurement that's guided our journey. We started with the moon, 1¼ light seconds away. We moved to the sun, 8 light minutes. Then to the outer solar system, a few light hours. Then to the nearest stars, a few light years. Then across the galaxy, tens of thousands of light years. Then to nearby galaxies, millions of light years. Then to distant clusters and superclusters, hundreds of millions or even billions of light years. And finally, we arrived at the edge of the observable universe, 13.8 billion light years in light travel time, 46 billion light years in actual distance today. The light year has taken us from the familiar to the unfathomable, from human scales to cosmic scales, from the present to the distant past. It's not just a unit of distance, it's a bridge between space and time, a tool for understanding how the universe works, a way to make sense of scales that would otherwise be impossible to grasp. And here's the truly beautiful thing about the light year, the reason it matters so much in astronomy. When we look out into space, we're not just seeing objects at various distances, we're seeing the history of the universe unfold before us. Every star, every galaxy, every cluster is a snapshot from a different era, a different moment in cosmic time. The nearest stars show us the recent past, a few years, Ergo, while the most distant galaxies show us the early universe, billions of years ago. By studying objects at different distances, astronomers can piece together a timeline of cosmic evolution, tracing how galaxies formed and grew, how stars were born and died, how the universe changed from a hot, dense state to the cool, vast expanse we see today. The light year is the key to this endeavor, the measuring stick that allows us to place events in their proper sequence and understand the grand narrative of the cosmos. Let's dive deeper into this concept of cosmic expansion, because it's one of the most counterintuitive and fascinating aspects of modern cosmology. When we say the universe is expanding, people often imagine galaxies flying apart through space, like debris from an explosion, moving through a pre-existing void. But that's not quite right. The galaxies aren't moving through space. Space itself is expanding, stretching like the surface of an inflating balloon, carrying galaxies along with it. Imagine drawing dots on a balloon and then inflating it. The dots move apart, not because they're traveling across the balloon's surface, but because the surface itself is getting bigger. That's what's happening with galaxies in the universe. They're embedded in space, and as space expands, they move apart, with the distance between them growing even though they're not actually moving in the conventional sense. This distinction becomes crucial when we talk about objects that are very far away. For nearby galaxies, the expansion of space doesn't matter much. Their distance changes so slowly that it's negligible on human timescales. But for distant galaxies, billions of light years away, the expansion is significant. In fact, at extreme distances, the expansion of space can make it seem like galaxies are moving away from us faster than the speed of light. Wait, didn't we say nothing can move faster than light? That's correct. Nothing can move through space faster than light. But space itself isn't bound by that rule. Space can expand as fast as it wants, and if two objects are far enough apart, the expansion of space between them can carry them away from each other at superluminal speeds. This doesn't violate relativity because the objects aren't actually moving through space at that speed. They're being carried along by the expansion of space itself, which is a completely different phenomenon. The expansion of space also affects the light traveling through it. As space expands, the wavelength of light traveling through that space gets stretched. A phenomenon called cosmological redshift. This is different from the Doppler shift you might be familiar with, where the motion of an object through space changes the frequency of light or sound waves. Cosmological redshift isn't due to motion. It's due to the expansion of space itself, stretching the light as it travels. The farther the light has traveled, the more space has expanded during its journey, and the more the light has been stretched. This is why distant galaxies appear redder than nearby ones. Their light has been shifted toward longer wavelengths, toward the red end of the spectrum, by the expansion of the universe. And by measuring how much a galaxy's light has been redshifted, astronomers can determine how far away it is and how long the light has been traveling, giving them a direct measurement of distance and look-back time. This expansion also has implications for the future. If dark energy continues to dominate, as current evidence suggests, the expansion will keep accelerating. Galaxies will move apart faster and faster, and eventually, distant galaxies will recede from us at speeds greater than the speed of light. At that point, their light will no longer be able to reach us. The photons will be emitted, but the space between us and them will be expanding so rapidly that the light can't make any progress toward us. It'll be like running on a treadmill that's speeding up faster than you can run. You're moving forward, but you're not getting anywhere. These galaxies will disappear from view, crossing a boundary called the cosmic event horizon, beyond which nothing can ever reach us, no matter how long we wait. In a sense, they'll be lost forever, cut off from our observable universe, existing in a region of space that we can never, ever see or interact with again. This raises a strange and somewhat melancholy thought. There are galaxies out there right now, galaxies we can see with our telescopes, that are already beyond the point where we could ever reach them, even if we traveled at the speed of light. The expansion of space has already carried them so far away that any signal we send toward them would never arrive. We can see their light because that light was emitted long ago, when the universe was smaller and they were closer. But if we tried to communicate with them, our message would never reach them. They're causally disconnected from us, existing in a part of the universe that's forever out of reach. And as time goes on, more and more galaxies will cross this boundary until eventually, billions of years in the future, only the galaxies in our local group will remain visible, and everything else will have disappeared beyond the horizon, leaving us in a small island of light surrounded by an ever-expanding ocean of darkness. But let's not dwell on the far future. Let's think about what all of this means for our understanding of distance and time. The light year, as a unit, encapsulates one of the most profound truths about the universe, that distance and time are fundamentally linked, woven together into a single fabric called space-time. You can't separate them. When you look at a distant object, you're not just seeing it at a particular distance. You're seeing it at a particular time. The two are inseparable. And this has been known since Einstein's theory of relativity, which showed that space and time are not separate, independent entities, but aspects of a single four-dimensional continuum. Events don't just happen at a location in space. They happen at a location in space-time, at a particular point in both space and time. And the speed of light is the conversion factor between space and time, the thing that ties them together into a unified whole. This is why the light year is such a natural unit for astronomy. It respects the deep connection between space and time, treating them as two sides of the same coin. When we say a star is 10 light years away, we're saying it's at a distance that light takes 10 years to cross. But we're also implicitly saying we're seeing that star as it was 10 years ago. The distance and the time are one and the same, just expressed in different units. And this unity of space and time is not just a mathematical convenience. It's a reflection of the actual structure of reality, the way the universe is put together at its most fundamental level. Space-time is the stage on which everything happens, the arena where matter and energy interact, where gravity curves and bends, where light travels and particles collide. And the light year is a unit that honors this reality, treating space and time not as separate things, but as a single, unified whole. There's also a philosophical dimension to all of this, a sense in which the light year forces us to confront the limits of our knowledge and our place in the cosmos. We live on a small planet orbiting an average star in a typical galaxy, located in an unremarkable part of the universe. There's nothing special about our location, nothing that singles us out as unique or privileged. And yet, because light takes time to travel, we occupy a unique position in time, seeing the universe from a particular moment in its history. Observers in other galaxies, looking back at us, would see the Milky Way as it was millions or billions of years ago, long before humans existed, perhaps even before the Earth formed. To them, we're part of the ancient past, a galaxy from a bygone era, frozen in time by the delay of light. And similarly, when we look at distant galaxies, we're seeing them as they were in the distant, past, as they existed long before our solar system even came into being. This creates a kind of cosmic loneliness, a realization that we're fundamentally separated from the rest of the universe, not just by distance, but by time. We can see distant galaxies, but we can never interact with them in any meaningful way. By the time we see them, they've already moved on, changed, evolved into something different. The light we're seeing is a message from the past, a postcard from a galaxy that no longer exists in the form we're observing. And this is true for everything we see: the stars in our own galaxy, the planets in our solar system, even the sun itself. Everything we observe is slightly out of date, delayed by the time it takes for light to travel. There is no such thing as observing the universe as it is right now. We can only see the universe as it was, and the farther out we look, the further back in time we see. And yet, this is also what makes astronomy so powerful and so beautiful. Because we can see the past, we can study the history of the universe directly. We don't have to rely on fossil records or geological strata. We can literally watch cosmic history unfold before our eyes, observing galaxies at different stages of their evolution, seeing stars being born and dying, watching the universe change and grow. The light year is the tool that makes this possible, the unit that connects distance and time, allowing us to place events in their proper historical context and understand the grand story of the cosmos. Without the light year, without this bridge between space and time, astronomy would be a very different science, perhaps an impossible one. Let's think about some specific examples to make this more concrete. When we observe a galaxy 1 billion light years away, we're seeing that galaxy as it was 1 billion years ago. But what's happening in that galaxy right now, at this very moment? We don't know. We can't know. The information about its current state is still traveling through space, and it won't reach us for another billion years. For all we know, that galaxy could have collided with another galaxy, triggering a burst of star formation. Or it could have fallen into a massive black hole, being torn apart and consumed. Or it could be essentially unchanged, continuing its slow evolution, gradually converting gas into stars and stars into black holes and white dwarfs. We have no way of knowing until the light from those events reaches us. And by the time it does, by the time we see what's happening in that galaxy now, it'll be 2 billion years in the future, and the galaxy will have moved on to yet another state that we won't see for billions of years more. This creates a kind of temporal mosaic, a patchwork view of the universe where every object exists at a different moment in time. The moon we see is 1¼ seconds old. The sun is 8 minutes old. Proxima Centauri is 4 years old. Andromeda is 2.5 million years old. The Virgo cluster is 55 million years old. Distant quasars are billions of years old. And the cosmic microwave background is 13.8 billion years old. All of these objects coexist in our observations, but they don't coexist in time. They're spread out across the history of the universe, each one representing a different era, a different chapter in the cosmic story. And by studying them together, we can piece together a coherent narrative, tracing the evolution of the universe from the Big Bang to the present, from the hot, dense plasma of the early cosmos to the cool, vast expanse filled with galaxies and stars that we see today. The light year also helps us appreciate the sheer scale of the universe in a way that other units of measurement simply can't. Miles and kilometers are fine for everyday distances, for measuring the size of countries or the distance between cities, but they quickly become unwieldy when we're talking about astronomical distances. Saying the Andromeda galaxy is 14 septillion miles away doesn't convey anything meaningful. The number is too large, too abstract. But saying it's 2.5 million light-years away, that the light we see left that galaxy 2.5 million years ago, that gives us something to hold on to, a timescale we can relate to, even if we can't fully comprehend it. 2.5 million years is still an incredibly long time, but it's a time we can at least imagine, a span of history we can think about in terms of human evolution and the development of civilization. It grounds the distance in something tangible, something connected to our experience, even if only distantly. And this is why the light year has become the standard unit of measurement in astronomy. It's not arbitrary. It's not just a convenient convention. It's a unit that reflects the deep structure of the universe, the intimate connection between space and time. And it allows us to talk about cosmic distances in a way that's both scientifically precise and philosophically meaningful. When we say a star is 100 light years away, we're making a statement about distance, yes, but we're also making a statement about history, about the past, about the journey that light has taken to reach us. We're acknowledging that the universe is not a static snapshot, but a dynamic, evolving entity, and that every observation we make is a window into a different moment in that evolution. There's also a humbling aspect to all of this. The universe is vast, far vaster than anything we encounter in our daily lives. Even the nearest stars are so distant that reaching them is currently beyond our technological capabilities. The Milky Way galaxy is so large that light takes 100,000 years to cross it. The observable universe is so enormous that light has been traveling for nearly 14 billion years and still hasn't reached us from the farthest regions. These are scales that dwarf human experience, that make our lives and our concerns seem incredibly small and insignificant in comparison. And yet, there's also something empowering about understanding these scales. Because by grasping the light year, by understanding how distance and time are connected, we're participating in one of humanity's greatest achievements, the project of understanding the universe and our place in it. We're reaching out with our minds, if not our bodies, to touch the farthest reaches of the cosmos, to explore regions of space and time that are unimaginably distant, and to bring that knowledge back to Earth, to share it, to learn from it, to let it inform how we see ourselves and our world. Let's think about the journey of a single photon, a particle of light, as it travels across cosmic distances. Imagine a photon being emitted from a star in a distant galaxy, 10 billion light years away. That photon begins its journey when the universe is only about 3 billion years old, less than a quarter of its current age. At the moment of emission, the photon is just one of countless trillions being released by the star, created through nuclear fusion in the star's core, worked its way up through layers of plasma, and finally escaped into space. Once free, the photon travels in a straight line, or as straight a line as possible given the curvature of space-time caused by massive objects along the way. It moves at the speed of light, always, never slowing down, never speeding up, just maintaining that constant, unwavering velocity of 186,000 miles per second. As the photon travels, it passes through the interstellar medium of its home galaxy, a thin gas of atoms and molecules and dust particles. Occasionally, it might interact with one of these particles, being absorbed and then re-emitted, or scattered in a new direction. But most of the time, it just passes through unimpeded, the distances between particles so vast that even a dense cloud of gas is mostly empty space. Eventually, the photon escapes the galaxy entirely, entering intergalactic space, a region even emptier than the interstellar medium. Here, there's on average less than 1 atom per cubic meter, a vacuum more perfect than anything we can create in a laboratory. The photon travels through this void for billions of years, decade after decade, century after century, millennium after millennium, crossing unimaginable distances, passing by other galaxies, sometimes close enough that their gravity bends its path slightly, causing a tiny deflection that changes its trajectory by a fraction of a degree. All the while, the universe is expanding. Space itself is stretching, and as it stretches, the photon's wavelength is stretched too. The photon was emitted as visible light, perhaps blue or green or red, but as it travels through expanding space, its wavelength increases, shifting toward the red end of the spectrum and then beyond, into the infrared. By the time it reaches the halfway point of its journey, 5 billion years after being emitted, the photon has been redshifted significantly. Its wavelength doubled or tripled compared to what it was at emission. And it keeps traveling, keeps moving through the void, crossing galaxy after galaxy, passing through clusters and superclusters, threading through the cosmic web, always maintaining its speed, always moving in its chosen direction, pulled along by the relentless march of time. Finally, after 10 billion years, after traveling across nearly the entire breadth of the observable universe, the photon approaches a small spiral galaxy located in a quiet corner of space. This galaxy, the Milky Way, wasn't even born when the photon began its journey. The gas and dust that would eventually form the Milky Way stars and planets were still scattered across space, only just beginning to coalesce under the influence of gravity. But now, 10 billion years later, the Milky Way is fully formed, a mature galaxy filled with hundreds of billions of stars. The photon enters the Milky Way, passes through its outer halo, crosses the disk, and finally, purely by chance, encounters a small yellow star orbited by 8 planets. The third planet from that star, a blue-green world covered mostly by water, happens to be in the photon's path. The photon enters the planet's atmosphere, passing through layers of nitrogen and oxygen, scattering off a few molecules along the way, but generally maintaining its course. And then, at the very end of its 10 billion year journey, the photon strikes a telescope mirror, focusing it onto a detector, where it's absorbed by a silicon chip and converted into an electrical signal. That signal is recorded, processed, analyzed by astronomers who study it, measure its wavelength, determine how much it's been redshifted, and calculate that it came from a galaxy 10 billion light years away. The photon's journey is over. It has delivered its message, a tiny piece of information about the state of the universe 10 billion years ago, and now it's gone, its energy absorbed, its existence ended. This is the reality of astronomy. Every observation we make, every image we capture, is the result of countless photons completing similar journeys, each one traveling for years or millennia or billions of years, carrying information across the cosmos, and finally arriving at Earth, where we can detect and study them. And each photon tells us something. It might tell us about the chemical composition of a distant star, revealed through the absorption lines in its spectrum. It might tell us about the motion of a galaxy, revealed through its redshift. It might tell us about the temperature of the cosmic microwave background, revealed through its wavelength and intensity. Every photon is a messenger, a carrier of information, and by collecting and analyzing millions or billions of these photons, astronomers can reconstruct the history and structure of the universe in incredible detail. But photons aren't the only messengers. In recent years, astronomers have opened up entirely new windows onto the universe through the detection of gravitational waves and neutrinos. Gravitational waves are ripples in spacetime itself, produced by violent cosmic events like the collision of black holes or neutron stars. These waves travel at the speed of light, just like photons, but they interact very weakly with matter, passing through planets and stars and galaxies without being absorbed or scattered. This makes them incredibly difficult to detect, but it also means they can carry information from regions of the universe that are opaque to light, like the centers of supernovae or the moments immediately following the Big Bang. Neutrinos are tiny, nearly massless particles produced in nuclear reactions, and they too interact very weakly with matter, allowing them to escape from the cores of stars and travel across the universe largely unimpeded. By detecting gravitational waves and neutrinos in addition to photons, astronomers are building a more complete picture of the cosmos, one that includes not just the light we can see, but also the invisible processes happening in the hearts of stars and the fabric of space-time itself. One of the most exciting developments in recent astronomy has been the detection of gravitational waves from merging black holes. In 2015, the LIGO Observatory detected the first ever gravitational wave signal, a ripple in space-time produced by two black holes colliding and merging together about 1.3 billion light-years away. The signal lasted only a fraction of a second, a brief chirp as the black holes spiraled together and combined into a single larger black hole. But that brief signal contained a wealth of information. It told astronomers the masses of the black holes, their spins, their distance, and the amount of energy released in the collision. Energy equivalent to about 3 solar masses, converted entirely into gravitational waves according to Einstein's famous equation, E equals mc squared. Since that first detection, LIGO and other gravitational wave observatories have detected dozens of similar events, revealing a population of massive black holes lurking in the universe, far more common than anyone had expected. These black holes are typically tens of times more massive than the Sun, and their collisions are among the most violent events in the universe, releasing more energy in a fraction of a second than all the stars in the observable universe combined. Gravitational waves from merging black holes that are billions of light-years away provide us with information about those events as they happened billions of years ago. Just like light, gravitational waves take time to travel, and the farther away the source, the older the information. When LIGO detected a signal from black holes merging 1.3 billion light-years away, it was observing an event that occurred 1.3 billion years in the past, back when the Earth was in the midst of the Proterozoic eon, and life was just beginning to evolve complex multicellular forms. The black holes themselves, by now, in the actual present moment, have long since merged and settled down, radiating away any remaining disturbances and becoming a single, quiet black hole. But we're only just now seeing, or rather feeling, the ripples from that ancient collision. The gravitational waves washing over us like the wake from a boat that passed by over 1 billion years ago. Neutrinos present a different kind of challenge. Unlike photons and gravitational waves, which travel at the speed of light, neutrinos have a tiny but non-zero mass, which means they travel slightly slower. However, for all practical purposes, neutrinos move at essentially the speed of light, close enough that the difference doesn't matter for most astronomical observations. What makes neutrinos special is their ability to pass through matter almost entirely unimpeded. A neutrino can pass through a light-year of solid lead without interacting. That's how weakly they interact with normal matter. This makes them incredibly difficult to detect because you need enormous detectors and you have to wait for a long time to catch even a few neutrinos. But it also makes them invaluable for studying processes that occur deep inside stars or in other extreme environments where light can't escape. The most famous example of neutrino astronomy came in 1987 when a supernova exploded in the Large Magellanic Cloud, about 160,000 light-years away. This supernova, designated SN 1987A, was the closest and brightest supernova observed in nearly 400 years, and it provided astronomers with a unique opportunity to study the explosion in detail. A few hours before the light from the supernova reached Earth, detectors in Japan and the United States recorded a burst of neutrinos, about 24 particles arriving over the course of a few seconds. These neutrinos had been produced in the core of the star during the collapse that triggered the supernova, and they escaped immediately, traveling through the collapsing star's outer layers without being absorbed. The light, on the other hand, took hours to work its way out of the dense stellar material, diffusing through the layers of gas before finally breaking free and beginning its journey to Earth. The fact that the neutrinos arrived first, ahead of the light, confirmed theoretical models of how supernovae work and provided direct evidence that neutrinos are produced in these explosions. But even with these new messengers, gravitational waves and neutrinos, we're still fundamentally limited by the speed of light. Information can't travel faster than that, so we're always seeing the universe as it was, never as it is. This is a fundamental constraint imposed by the laws of physics, specifically by the structure of space-time and the theory of relativity. In relativity, there's no such thing as absolute simultaneity, no universal now that applies everywhere in the universe. Different observers, moving at different speeds or located at different positions in a gravitational field, will disagree about what events are happening at the same time. The only thing everyone agrees on is the speed of light, which is the same for all observers regardless of their motion. And this universal speed limit, this cosmic speed limit, is what creates the light year, the natural unit for measuring distances in a universe where information propagates at a finite speed. Some people wonder if there might be ways to get around this limit, to travel faster than light, or to send information across vast distances instantaneously. Science fiction is full of ideas like warp drives, wormholes, and quantum entanglement-based communication. But so far, none of these ideas have panned out in a way that would allow practical faster-than-light travel or communication. Warp drives, which involve contracting space in front of a spaceship and expanding it behind, are theoretically possible according to general relativity, but they require exotic forms of matter with negative energy density, something that has never been observed and may not exist. Wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe, are also theoretically possible, but require similar exotic matter to keep them open and stable. And quantum entanglement, while a real phenomenon, doesn't allow for faster-than-light communication because you can't use it to send information. The correlations between entangled particles are random, and you can only see the pattern by comparing measurements after the fact, using conventional, slower-than-light communication. So for now, and likely for the foreseeable future, we're stuck with the speed of light as the ultimate speed limit, and the light year as the natural unit for measuring cosmic distances. And that's okay. In fact, it's more than okay. It's beautiful, because the light year isn't just a practical tool. It's a reminder of how the universe works, of the deep connection between space and time, of the way information propagates through the cosmos, and of our place in the grand scheme of things. We're observers, watching the universe unfold, seeing its history play out in the light that reaches us from distant stars and galaxies, piecing together the story of how we got here and where we're going. There's something profound about the way light acts as a time machine, showing us not the universe as it is, but as it was. Every star you see in the night sky is a glimpse into the past. Every galaxy captured by the Hubble or James Webb Space Telescope is a window into history. And this isn't just true for distant objects, it's true for everything. When you look at your friend sitting across from you, you're seeing them as they were a few nanoseconds ago, the time it took for light to travel from them to your eyes. When you look at the moon, you're seeing it as it was 1.3 seconds ago. When you look at the sun, you're seeing it as it was 8 minutes ago. The entire universe, from the closest to the farthest, exists for us only in the past, a collection of memories frozen in light, traveling toward us across space and time. This creates a kind of layered reality where different parts of the universe exist at different moments in their history. The star you see tonight might have already exploded, its light snuffed out, its planets vaporized, but you won't know about it until years or decades or centuries from now, when the light from that explosion finally reaches Earth. The galaxy you observe through a telescope might have been consumed by a larger galaxy, its stars ripped away and scattered, but you're still seeing it as it was millions of years ago, intact and whole, because that's when the light you're seeing left that galaxy. And this disconnect between observation and reality, this gap between what we see and what actually is, forces us to think carefully about what we mean when we talk about the present moment, about what's happening now in the universe. Because there is no universal now, no single moment that encompasses all of space. The present is local, tied to our specific location in space-time, and anything beyond our immediate vicinity exists for us only in the past. But this isn't a limitation, it's an opportunity, because by studying light from different distances, astronomers can watch cosmic evolution unfold, observing galaxies at various stages of their development, seeing how they change over billions of years. Nearby galaxies show us what mature galaxies look like after billions of years of evolution. Intermediate distance galaxies show us galaxies in their middle age, still forming stars but settling down. Distant galaxies show us galaxies in their youth, wild and chaotic, full of hot young stars and undergoing rapid growth. And the most distant galaxies, the ones we can barely detect even with our most powerful telescopes, show us galaxies just beginning to form, emerging from the primordial gas that filled the early universe. By comparing these different snapshots, astronomers can trace the life cycle of galaxies, understanding how they're born, how they evolve, and how they eventually die, their star formation ceasing, their gas depleted, leaving behind a population of aging stars slowly fading into darkness. This technique, called cosmic archaeology, is one of the most powerful tools in modern astronomy. It allows scientists to study processes that take billions of years, far longer than any human lifetime or even the entire span of recorded history. By looking at objects at different distances, and thus at different times in the past, astronomers can effectively watch the universe evolve, seeing changes that would otherwise be impossible to observe. It's like having a time-lapse camera that captures the entire history of the cosmos, from the Big Bang to the present, with each frame representing a different epoch, a different stage in the grand story of creation and destruction that's been playing out for nearly 14 billion years. And the light year is the key to making this work. Without the light year, without a unit that connects distance and time, cosmic archaeology would be impossible. We'd have no way to place our observations in their proper historical context, no way to know whether we're looking at a young galaxy or an old one, a nearby star or a distant one. The light year gives us that context. It tells us not just where something is, but when it was, creating a map of the universe that's also a timeline, a four-dimensional picture of space-time that shows both the spatial distribution of matter and the temporal evolution of cosmic structures. Let's zoom back in now, bringing the scale down from the edges of the observable universe to something more tangible, more human, because while the light year is perfect for measuring cosmic distances, it's also useful for understanding our place in the universe and how isolated or connected we are to the rest of the cosmos. Consider this. The nearest star, Proxima Centauri, is 4.24 light years away. If we could build a spaceship that traveled at 10% of the speed of light, which is far beyond our current technology, but theoretically possible with future advances, it would take about 42 years to reach Proxima. That's a single human lifetime, just barely feasible if we're willing to commit to a one-way journey with colonists who would spend their entire lives traveling through space. But that's just to reach the nearest star. To reach Sirius, 8.6 light years away, would take 86 years at 10% light speed. To reach Vega, 25 light years away, would take 250 years, longer than the United States has existed as a nation. To reach the center of the galaxy would take 260,000 years. To reach Andromeda would take 25 million years. These are timescales that dwarf human civilization, that make interstellar travel seem not just difficult, but essentially impossible, at least with anything resembling current technology. And yet, humans have always been explorers, always pushing the boundaries of what's possible, always reaching for the next horizon. We've crossed oceans, climbed mountains, explored deserts and jungles and polar ice caps. We've sent probes to every planet in the solar system and beyond, venturing into the outer reaches where the sun's light is faint and the cold is almost absolute. We've landed on the moon, placed rovers on Mars, and flown spacecraft past Pluto and into interstellar space. The Voyager probes, launched in the 1970s, are now over 15 billion miles from Earth, so far away that it takes over 20 hours for a signal from them to reach us, traveling at the speed of light. They've crossed the boundary where the sun's influence ends and interstellar space begins, entering a realm where the solar wind gives way to the interstellar medium, where our sun is just another star in the sky, no brighter or more important than any other. And yet, even after all this time, even after traveling for over 40 years, the Voyager probes are still nowhere near the nearest star. At their current speed, it would take them over 70,000 years to reach Proxima Centauri, assuming they were heading in that direction, which they're not. Space is vast, and even our fastest spacecraft are painfully slow compared to the distances involved. But that hasn't stopped us from dreaming. Projects like Breakthrough Starshot are working on concepts for tiny, lightweight spacecraft that could be accelerated to a significant fraction of the speed of light using powerful lasers. These craft, called light sails, would be pushed by beams of laser light, gradually accelerating until they reach speeds of 20% of the speed of light, or even faster. At that velocity, they could reach Proxima Centauri in about 20 years, sending back images and data from another star system within a single human lifetime. It's an ambitious project, fraught with technical challenges, but it's not impossible. And if it succeeds, it would represent a monumental achievement, the first time humanity has sent a probe beyond the solar system to another star, bridging the light years that separate us from our cosmic neighbors. Even without physical travel, we've reached out into the cosmos in other ways. We've sent radio signals into space, messages intended for any intelligent civilizations that might be listening. The Arecibo message, broadcast in 1974, was a powerful radio transmission aimed at the globular cluster M13, about 25,000 light-years away. That message is still traveling through space, moving at the speed of light, and won't reach its destination for another 23,000 years. And even if there's someone there to receive it, and even if they respond immediately, we won't get the reply for another 25,000 years. That's a conversation with a 50,000-year lag, a timescale that makes communication across interstellar distances seem absurd. And yet, we did it anyway, because it's in our nature to reach out, to make contact, to say, here we are, we exist, and we want to know if you're out there too. This impulse to explore and communicate, to push beyond our boundaries and reach for the stars, is one of the defining characteristics of humanity. It's what drove us out of Africa tens of thousands of years ago, spreading across the globe, settling every continent, adapting to every climate. It's what drove us to build ships and sail across oceans, to construct telescopes and peer into the heavens, to develop rockets and leave the Earth behind. And it's what will drive us, if we survive, to eventually venture beyond the solar system, to cross the light years that separate us from other stars, and to explore the galaxy in person. It might take centuries or millennia. It might require technologies we can't even imagine yet. But if history is any guide, we'll get there eventually, because that's what we do. We explore, we expand, we reach for the unknown. And while we're waiting for the technology to catch up to our ambitions, we can still explore the universe with our telescopes, our satellites, our detectors, gathering light from the farthest reaches of space and using it to understand where we came from and where we're going. The light year is our guide in this endeavor, the measuring stick that allows us to navigate the cosmos, to place ourselves in context, and to appreciate the sheer scale of the universe we inhabit. It's a unit that reminds us we're part of something vast, something ancient, something that existed long before we did and will continue long after we're gone. And yet, despite our insignificance in the grand scheme of things, we're still able to look up at the night sky, to see the light from distant stars and galaxies, and to understand what we're seeing, to know that we're looking back in time, witnessing the history of the universe unfold before our eyes. There's a beauty in that, a sense of wonder and awe that comes from understanding our place in the cosmos. We're made of stardust, quite literally. The atoms in our bodies, the carbon and oxygen and nitrogen, the iron in our blood, all of it was forged in the cores of stars that lived and died billions of years ago, scattering their enriched material into space, where it eventually coalesced into new stars and planets, including our own sun and Earth. We're the universe looking at itself, a way for the cosmos to know itself, to understand itself, to appreciate its own beauty and complexity. And the light year is part of that understanding, a tool that connects us to the vastness of space and time, allowing us to see ourselves not as isolated individuals on a tiny planet, but as part of a cosmic story that spans billions of years and countless light years. When you look up at the night sky, you're seeing history. You're seeing light that has traveled for years or centuries or millennia or billions of years, carrying information from distant times and places. You're seeing the universe not as it is, but as it was, a collection of frozen moments, each one a snapshot from a different era. And in a strange way, you're also seeing the future, because the light that's leaving distant galaxies right now, light that won't reach Earth for billions of years, will someday tell future astronomers about the universe as it existed in our time. We're part of that story too, emitting light into space, sending radio signals and television broadcasts that radiate out at the speed of light, creating an expanding bubble of electromagnetic radiation that carries information about human civilization. Someday, billions of years from now, if there's anyone out there to receive it, that light might reach another world, another civilization, and they'll look at it and wonder about us, about who we were and what we were like, just as we wonder about the distant galaxies whose light is now reaching us from the ancient past. So let's bring this all together. Let's think about what we've learned on this journey through the light year, from the smallest scales to the largest, from the moon to the edge of the observable universe. We've covered a lot of ground, or rather, a lot of space and time, and it's worth taking a moment to reflect on what it all means, what lessons we can draw from this exploration of distance and history and the fundamental structure of the cosmos. First, we've learned that distance and time are inseparable. You can't talk about one without the other. When you measure how far away something is in the universe, you're also measuring how long it took for light to reach you, which means you're measuring how far back in time you're looking. The light year embodies this connection, treating space and time as two aspects of a single unified reality, space-time, the four-dimensional fabric in which all events occur. This isn't just a mathematical abstraction. It's the actual structure of the universe, the way reality is put together at its most fundamental level. And understanding this connection helps us make sense of the cosmos in a way that would be impossible if we thought of space and time as separate, independent things. Second, we've learned that the universe is vast beyond comprehension. Even the nearest stars are so far away that reaching them is currently beyond our capabilities. The galaxy is so large that light takes 100,000 years to cross it. The observable universe is so enormous that light has been traveling for nearly 14 billion years and still hasn't reached us from the farthest regions. These are scales that dwarf human experience, that make our lives and our planet seem incredibly small and insignificant in comparison. And yet, there's something empowering about understanding these scales, about grasping just how big the universe is. It puts our problems in perspective. It reminds us that we're part of something much larger than ourselves, something ancient and vast and full of mystery. And it gives us a sense of wonder, a feeling of awe at the sheer magnitude of creation. Third, we've learned that we're fundamentally observers of the past. There's no way to see the universe as it is right now. We can only see it as it was at various points in history, depending on how far away we're looking. The moon shows us the past from 1 second ago. The sun shows us the past from 8 minutes ago. Proxima Centauri shows us the past from 4 years ago. Andromeda shows us the past from 2.5 million years ago. The cosmic microwave background shows us the past from 13.8 billion years ago. And by studying these different snapshots, by comparing observations at different distances, astronomers can piece together the history of the universe, tracing its evolution from the hot, dense state shortly after the Big Bang to the cool, vast expanse we see today. The light year makes this possible, giving us a way to map not just the spatial distribution of matter, but also its temporal evolution, creating a four-dimensional picture of the cosmos that reveals how structures formed, how galaxies grew, and how the universe changed over billions of years. Fourth, we've learned that light is more than just something that allows us to see. It's a messenger, carrying information across the cosmos, connecting us to distant places and times, allowing us to study objects we could never reach physically. Every photon tells a story. It might tell us about the temperature of a star, the composition of a planet's atmosphere, the speed of a galaxy, or the density of the early universe. By collecting and analyzing these photons, astronomers can reconstruct the history and structure of the cosmos in incredible detail, answering questions about where we came from, how the universe works, and what the future might hold. And it's not just photons. Gravitational waves and neutrinos are also messengers, carrying information from regions and events that are opaque to light, giving us a more complete picture of the universe and its processes. Fifth, we've learned that the universe is not static. It's expanding, with space itself stretching, carrying galaxies apart. This expansion was one of the great discoveries of the 20th century, completely changing our understanding of the cosmos and revealing that the universe has a history, a beginning, and potentially an end. The expansion also affects how we measure distance, because objects that are very far away are receding from us due to the stretching of space, and the light from those objects is redshifted, its wavelength stretched by the expansion. By measuring this redshift, astronomers can determine how far away an object is and how long its light has been traveling, giving them a direct measurement of distance and time. And the expansion is accelerating, driven by a mysterious force called dark energy, which is pushing galaxies apart faster and faster, eventually to the point where distant galaxies will recede from us at speeds greater than light and disappear beyond our horizon, forever out of reach. Sixth, we've learned that there are limits to our knowledge. We can only see the observable universe, the region of space from which light has had time to reach us since the Big Bang. Beyond that, there's the rest of the universe, potentially infinite in extent, filled with galaxies and stars and planets we can never observe, forever hidden beyond the horizon. And even within the observable universe, there are things we don't understand. Dark matter and dark energy together make up 95% of the universe, and we don't know what either of them is. We have theories, models, ideas, but no definitive answers. And there are deeper mysteries too, questions about the nature of time, the origin of the Big Bang, the possibility of other universes, and the ultimate fate of the cosmos. These questions remain unanswered, and they may always remain unanswered, reminding us that despite all our advances in science and technology, there's still so much we don't know, so much that remains mysterious and unknown. But here's the thing. These limits, these mysteries, these unanswered questions, they don't diminish the beauty and wonder of the universe. If anything, they enhance it. They remind us that the cosmos is vast and complex and full of surprises, that there's always more to discover, always new questions to ask, always deeper levels of understanding to achieve. And the light year is our tool for navigating this vast, mysterious universe, the unit that allows us to measure cosmic distances, to place events in their proper historical context, and to appreciate the sheer scale of creation. It's a simple concept, really. The distance light travels in 1 year, but it opens up the entire cosmos, allowing us to explore galaxies billions of light years away, to see the universe as it was billions of years in the past, and to understand our place in the grand scheme of things. And what is our place? We're inhabitants of a small planet orbiting an average star in a typical galaxy, located in an unremarkable part of the universe. There's nothing special about our location, nothing that singles us out as unique or privileged, and yet we're also observers, conscious beings capable of looking up at the night sky, of wondering about the stars, of asking questions about where we came from and where we're going. We're the universe looking at itself, a way for the cosmos to know itself, to understand itself, to appreciate its own beauty and complexity. And in that sense, we are special, time, ones. Not because of where we are, but because of what we can do, because of our ability to think and reason and discover, to push the boundaries of knowledge and explore the unknown. The light year connects us to that larger universe, bridging the gap between our small local experience and the vast cosmic scale. When you look up at the night sky and see a star, you're not just seeing a point of light, you're seeing a sun, perhaps surrounded by planets, perhaps home to life, perhaps the birthplace of civilizations we can only imagine. And you're seeing it not as it is now, but as it was years or decades or centuries ago, the light having traveled across space and time to reach you. That light is a message from the past, a connection to a distant place and time. And by understanding what you're seeing, by knowing that the light has been traveling for years and that the star has moved on, changed, evolved since that light was emitted, you're participating in the grand project of understanding the cosmos, of figuring out how it works and what it all means. There's a poetry to this, a beauty in the way light connects us to the universe, allowing us to see across vast distances and back through time. Every photon that hits your eye has a story, a journey it's completed, crossing the void between stars, passing through clouds of gas and dust, dodging asteroids and comets, threading through the cosmic web, and finally reaching Earth, where you, a conscious being on a small blue planet, can detect it, study it, learn from it. And that photon, in a very real sense, connects you to the star that emitted it, creating a link across the light years that separate you, a connection that transcends distance and time and makes you part of a larger cosmic community, even if that community is spread across billions of light years and billions of years of history. And this is why the light year matters. It's not just a unit of measurement, it's a reminder of our place in the universe, of the vastness of space and time, and of the incredible journey that light makes to reach us from distant stars and galaxies. It's a tool that allows us to explore the cosmos, to study its history, and to understand our own origins. It's a bridge between the familiar and the unfathomable, between the human scale and the cosmic scale, between the present and the distant past. And it's a symbol of our curiosity, our desire to understand, our drive to explore and discover and push the boundaries of knowledge. When we talk about light years, we're not just talking about distance. We're talking about history, about connection, about the fundamental structure of reality, and about our place in the grand cosmic story that's been unfolding for nearly 14 billion years. So the next time you look up at the night sky, remember that you're seeing light that has traveled across the light years to reach you. Every star is a window into the past, every galaxy a glimpse of history, every photon a messenger carrying information from distant places and times. And remember too that you're part of this cosmic story, made of stardust, connected to the universe in ways both profound and beautiful. The light year is your guide, your tool for understanding the vastness of space and time, and your reminder that despite how small you might feel in the face of such enormity, you're still capable of grasping it, of understanding it, of appreciating the beauty and wonder of the cosmos. That's the real magic of the light year. It doesn't just measure distance, it connects us to the universe, bridging the gap between our tiny human experience and the infinite expanse of creation, and reminding us that we're part of something much, much larger than ourselves. And if this journey through the light year has taught us anything, it's that the universe is worth understanding, worth exploring, worth contemplating. It's vast and ancient and full of mystery, but it's also beautiful and ordered and comprehensible, governed by laws we can discover and understand. The light year is proof of that. It's a simple concept that emerges from the fundamental properties of light and the structure of space-time, and yet it allows us to navigate the entire observable universe, to place events in their proper context, and to trace the history of the cosmos from the Big Bang to the present. That's an incredible achievement, a testament to human curiosity and ingenuity, and a reminder that no matter how big the universe is, no matter how distant the stars, we're still capable of reaching them, if not with our bodies, then at least with our minds, using tools like the light year to bridge the vast distances and connect ourselves to the cosmos. So take a moment tonight, or the next clear night you have, and go outside. Look up at the stars, find a constellation you recognize, or just pick a bright star at random, and think about the light you're seeing, the journey it's made to reach you. Think about the years or decades or centuries it's been traveling, crossing the void between stars, maintaining its speed and direction, carrying information from the distant past. Think about the star itself, what it might be like, whether it's still there or whether it's already gone, exploded or faded, its light still traveling through space, a ghost of a star that no longer exists. And think about yourself, standing on a small planet orbiting an average star, looking up at the night sky and contemplating the universe, participating in the grand project of understanding the cosmos. In that moment, you're connected to the universe in a very real way, linked by light across the light years, part of a cosmic story that spans billions of years and countless trillions of miles. And that connection, that understanding, that sense of wonder and awe, that's the real gift of the light year. It's not just a unit of measurement. It's a bridge to the stars, a window into history, and a reminder of our place in the vast, beautiful, mysterious universe we call home. If you've enjoyed this journey through the cosmos, if you found yourself thinking differently about the night sky, if the light year has broken your brain in the best possible way, consider sharing this with someone you love. Tell them about the distances we've covered, the scales we've explored, the connections we've made, and maybe, just maybe, they'll look up at the stars with new eyes, seeing not just points of light, but windows into the past, messengers from distant times and places, carrying stories across the light years to reach us here on Earth. Thank you for joining me on this journey. May your nights be filled with stars, your mind filled with wonder, and your heart filled with the knowledge that you're part of something vast and ancient and beautiful. Until next time, keep looking up, keep wondering, and keep exploring the infinite cosmos that surrounds us all. Sleep well and dream of the stars. Before we close, let's explore a few more fascinating aspects of light and distance that really drive home just how strange and wonderful the universe is. Consider the concept of a light echo, a phenomenon that occurs when light from a sudden, bright event, like a supernova, reflects off clouds of dust and gas surrounding the source. The direct light from the explosion reaches us first, traveling in a straight line at the speed of light, but some of the light travels a longer path, bouncing off nearby dust clouds before heading toward Earth. This reflected light arrives later, creating an echo, a delayed image of the original event. By studying these light echoes, astronomers can see the same explosion from multiple angles, piecing together a three-dimensional view of what happened. It's like watching an instant replay from different camera positions, except the cameras are clouds of dust scattered across light years of space, and the replay is delayed by months or years depending on the geometry of the reflecting material. One famous example of a light echo comes from a star called V838 Monochrotis, which underwent a dramatic brightening event in 2002. The star suddenly became one of the brightest in the Milky Way, though it was still too faint to see with the naked eye from Earth due to its distance of about 20,000 light years. As the light from this outburst traveled outward, it illuminated successive shells of dust that the star had ejected in previous episodes, creating a beautiful expanding ring of light that Hubble captured in a series of stunning images. These light echoes revealed details about the star's past, showing that it had undergone multiple outbursts over the years, each one shedding material into space that later reflected the light from subsequent events. It was a reminder that stars have histories, that they change over time, and that by carefully studying the light they emit, we can reconstruct those histories even across vast distances. Another strange phenomenon related to light travel time is the concept of a gravitational lens, which occurs when a massive object like a galaxy or cluster of galaxies bends the path of light from a more distant source. According to Einstein's general relativity, massive objects curve space-time, and light, which always travels in a straight line through space-time, follows those curves. From our perspective, it looks like the light has been bent or deflected, and in some cases, this bending can create multiple images of the same distant object, stretched and distorted into arcs or rings. But here's where it gets interesting. Because the light takes different paths around the lensing object, traveling different distances, the multiple images we see don't just show the same object from different angles. They show it at different times. One path might be slightly shorter than another, meaning the light arrives a few days or weeks earlier. So we see the source as it was a few days or weeks earlier in that image compared to the other images. In some cases, astronomers have observed supernovae that were gravitationally lensed, seeing the same explosion multiple times as the light traveled along different paths around the lensing galaxy. And in one remarkable case, they were able to predict when the next image would appear based on calculations of the different light travel times. And sure enough, it showed up right on schedule, providing a beautiful confirmation of general relativity and our understanding of how light behaves in curved spacetime. This interplay between light, gravity, and time creates opportunities for some truly mind-bending observations. Consider a quasar, a supermassive black hole at the center of a distant galaxy, feeding on nearby gas and shining brightly across the electromagnetic spectrum. Now imagine that quasar is being gravitationally lensed by a foreground galaxy, creating 4 separate images of the quasar arranged in a cross pattern around the lensing galaxy. Each image shows the quasar at a slightly different time, because the light has traveled along different paths of different lengths. If the quasar suddenly brightens due to a change in its accretion rate, that brightening will appear in one image first, then in another a few days or weeks later, then in the third, and finally in the fourth. By carefully monitoring these images and measuring the time delays between them, astronomers can do some incredibly cool things. They can measure the mass of the lensing galaxy with high precision. They can study the structure of spacetime around the lens, and they can even measure the expansion rate of the universe because the time delays depend on both the geometry of the lens and the overall expansion of space. It's a technique that turns gravitational lensing into a cosmic laboratory, using light travel time as a tool for probing the fundamental properties of the universe. These examples illustrate just how rich and complex the universe becomes when you start thinking seriously about light travel time and the finite speed of light. Every observation we make is not just a snapshot of a particular place, but a snapshot of a particular moment in time. And by carefully analyzing the light we receive, we can tease out information about distances, masses, expansion rates, and the history of cosmic objects. The light year is more than just a unit of distance. It's a window into the workings of the universe, a tool for exploring the relationship between space and time, and a reminder that in astronomy, every observation is a journey into the past. It's also worth thinking about the future of astronomy and how our understanding of the light year and cosmic distances might evolve. Right now, we're limited to observing electromagnetic radiation, gravitational waves, and neutrinos. But there might be other messengers we haven't discovered yet, other ways that information propagates through the universe. Some theories predict the existence of exotic particles like axions or magnetic monopoles that could carry information across cosmic distances. Others suggest that cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe, might create distinct